Hello everyone, my name is Liakos and I am affiliated with the National Observatory of Athens. I will be presenting the NELIOTA project that concerns the long-term monitoring of the Moon for detections of lunar impact flashes due to meteoroid and near-Earth objects collisions on the lunar surface. NELIOTA is the acronym of the words Near-Earth Objects, Lunar Impacts and Optical Transients. It is a collaboration between the European Space Agency and National Observatory of Athens in the framework of the Space Situational Awareness Program of ESA. The PI of the project from the Greek side is Dr. Alkis Tibonnanos, while Dr. Kosny and Dr. Moisl are the stakeholders from the ESA's side. The project started on early 2015 and the first 1.5 years was spent for the telescope upgrade and the software development. This period was followed by a 6-month testing period, while on February 2017, the campaign started officially. The first observing period lasted until January 2019 and was followed by a 2-year extension of the program. That is the second observing period, which lasted until January 2021. Between January and May 2021, we continued the observations while pending for another extension, which began officially on June 2021 and will last until mid-2023 with the NELIOTA team as a collaborator of the ESA Carmen project. For the needs of the project, we employ the 1.2-meter telescope at Cryoneri and a twin camera system. Each camera is equipped with a different photometric filter and we observe in R and I bands. Moreover, a 36 terabyte storage capacity is available for storing the data. The main goal of the project concerns the size-frequency distribution of meteoroids and small near-Earth objects in the vicinity of the Earth. These statistics will supply the space industry with valuable information about the satellite and space mission shielding, as well as for future lunar bases establishment. For the observations of NELIOTA, we apply the following strategy. We observe the night side of the Moon during the 10 and 45% of illumination phases, which corresponds to 5 to 8 nights per month. We observe simultaneously in R and I bands with a frame rate of 30 frames per second. Our setup provides a mean coverage of lunar area of approximately 3 million square kilometers. The data reduction is made with a dedicated software pipeline that was developed for the project's purposes. The software automatically performs the image calibration, subtracts the lunar background from the images, and detects potential events. Then, an expert user evaluates the detected events by visual inspection in order to exclude artifacts such as satellites and cosmic rays. The evaluation follows the flowchart shown in your screens. There are 2 main criteria. The first one concerns the detection in both cameras and in the same lunar area, and the second one concerns the stillness of the event between successive frames. Real events satisfy both criteria, while those that they don't are further characterized as suspected flashes. For the real and the suspected flashes, we apply the aperture photometry technique, and using standard stars, we are able to calculate the magnitude of the flashes. Using high detailed maps of the Moon, we also perform the localization of the flashes. Finally, within 24 hours of observations, we upload our results into the project's website. In this video, you see the flash on the upper left side and its evolution in time. However, as the flash evolves, you watch also that 2 diagrams are forming. The upper one is the temperature versus time, which in other words is the cooling curve of the flash. The lower diagram includes the light curve for each band. Therefore, for each set of R and I points, we can calculate the respective temperature using the R-I index. Finally, you may notice that after the fourth frame, the flash was recorded only in the I band because it became too cool to be recorded in R band as well. On the left side of your screens, you see the brightest lunar impact flash ever recorded by NELIOTA and its evolution in 5 successive frames. On the right side, you may watch a video of the most slow lunar impact flash ever recorded by NELIOTA that lasted approximately 360 milliseconds. In this slide, we can see the statistics of the NELIOTA project. The upper left plot shows the validated flashes detections by NELIOTA to date, while the lower left plot shows the respective observation hours. We have detected so far 137 validated flashes in approximately 203 hours of observations. The right plots show the magnitude distribution of the validated flashes in R and I bands, respectively. This is the map of the moon on which we have placed the NELIOTA detections to date. The crosses denote the validated flashes, while the filled circles denote the suspected ones, which are those that were detected only in the infrared camera's frames. The latter ones, however, as you can see, are not negligible, and approximately 1 out of 3 flashes are characterized as suspected. Yellow symbols denote the sporadic flashes, while the others, those which were associated with active meteoroid streams during the time of the observations. This is the brief formalism we follow for calculating the parameters of the meteoroids. The flux of the flash is based on the calculated magnitude of each band and is used for the derivation of the respective luminous energy. These energies are added together to derive the total luminous energy of the flash. There are 2 main critical parameters for which we have to make some assumptions in order to calculate the rest of them. The first one is the luminous efficiency eta, which is the ratio of the luminous over the kinetic energy and has been estimated from meteor showers on Earth and meteoroid impacts on Moon during meteoroid streams. The second one is the velocity of the meteoroids, which is accurate enough only for those that are connected to a stream, while that of sporadics has a wider range. Now, using the 2 extreme values of eta as suggested from other researchers, the masses of the meteoroids range from a few grams up to several hundreds of grams. However, using typical values of eta, the majority of the meteoroids have masses of a few hundred grams and diameters of a few centimeters. The temperature of the flashes are calculated using the black bodies approximation and the fluxes from the R and I bands. The majority of the flashes show temperatures between 2000 and 4500 kelvins. The majority of the craters have dimensions of a few meters, which is very difficult to be recorded by lunar orbiting missions such as LRO. The table on your left includes the meteoroid impact frequencies on Moon. The upper value concerns the case we take into account only the sporadic ones, while the lower value is the frequency during the streams. As you can see, the appearance rate is more than double when the Earth-Moon system enters the streams. If we extrapolate these frequencies on Earth, we can calculate the respective meteoroid flux rates for various distances from the Earth's surface for both normal periods of time or during the meteoroid streams. The diagram on the right shows the increase of the appearance rate as we move outwards the Earth's limits. At this point, I would like to remind you that these statistics can be used from the space industry for the satellite shielding as well as for the future lunar bases establishment. course, there are also other groups that monitor lunar impact flashes. The most important ones among them is that of NASA and the MIDAS project from Spain. The common characteristics of these programs concern the use of small-sized telescopes and the unfiltered or single-band observations. However, none of these groups publish online their results like NELIOTA does. The NASA group has announced 443 lunar impact flashes within a 15-year time period, but there are not any online details. Therefore, the detection rate was calculated based on one paper by Sachs et al. In 2014 that included a list with 126 flashes. The second rate was given by another team from the United States. Based on the findings of NELIOTA, we see that the detection rate of lunar impact flashes has been at least doubled or tripled if we take into account the suspected flashes too, and furthermore, we detect 2 magnitude fainter flashes in comparison with the NASA team that corresponds to 1 order of magnitude in mass. Finally, I will leave you with the summary of the work regarding the physical parameters and the appearance frequency distributions of the meteoroids in the vicinity of the Earth and the temperature of the flashes. Thank you all for watching, and I will be available for answering your questions. Thank you very much.